$135 million. That is the staggering price of a single F-35 Lightning II, the most advanced fifth-generation stealth fighter jet in existence. It is a flying supercomputer designed to vanish from enemy radar screens and dominate the skies with lethal pinpoint efficiency and unmatched electronic warfare capabilities. But beneath its skin of high-tech radar-absorbent material lies a shadow that challenges everything we believe about the absolute cutting edge of modern aerial warfare. The brain of this billion-dollar weapon system does not run on the latest 3-nanometer silicon from technology giants like Apple, Nvidia, or the foundries of TSMC, the core processor directing its weapon stealth profiles. And flight controls relies on an ancient relic in the computing world, a chip architecture nearly 20 years old. Welcome to the world of fossilized stability, a structural reality where the world's most sophisticated hardware depends on obsolete components to survive the extreme heat of battle. In this video, we will decode the terrifying paradox inside the F-35's brain and the hidden Achilles heel of the global military semiconductor supply chain. We explore the desperate multi-billion-dollar race to perform a total brain transplant before it is too late for the West's most critical air defense asset. To understand why the Pentagon intentionally freezes its technology in time, you must look at the brutal physics of survival at 30,000 feet above Earth. The F-35 relies entirely on sensor fusion, a system that collects massive streams of data from radar, thermal cameras, and electronic warfare suites to create one picture. This heavy lifting is managed by the integrated core processor known as the ICP, which serves as the central nervous system of the world's deadliest fighter jet. You might ask, why not swap this outdated processor for a commercial chip? It is faster, significantly cheaper, and uses far less electrical power during operation. The answer is cosmic radiation. At high altitudes, the atmosphere thins out, leaving sensitive commercial electronics bombarded by intense cosmic rays from the depths of space. On a cutting-edge 3-nanometer commercial chip, transistors are so microscopic that a single stray cosmic particle can flip a digital bit from a 0 to a 1. This tiny event causes an instant system crash. In mid-air combat, a single silicon freeze turns a $100 million fighter jet into a very expensive, unguided glider. This is why military chips are radiation-hardened. They are built on ancient, larger processes like 65 or 90 nanometers, providing the physical space needed for safety. Their massive size provides the armored structural space needed to absorb radiation interference and survive intense G-forces or extreme temperature, swings of supersonic flight operations. Reliability is the only currency that matters in survival, but it creates a dangerous economic loop known as the life cycle trap in military technology development. A fifth-generation weapon system takes 20 years to move from the initial drawing board to full-scale mass production and deployment to frontline combat units. When the F-35 program began in 2001, its silicon architecture was the absolute pinnacle of technology, light years ahead of any potential adversary in the world. But while the civilian commercial market went through 15 generations of smartphones, every 18 months the military tech cycle remained frozen for 2 decades to guarantee certification. This creates a critical supply chain crisis. By the time the F-35 reached full production, the companies that manufactured its original silicon had already shut down. Incredibly, the Department of Defense is often forced to hunt for legacy spare parts on eBay or pay commercial foundries millions to keep obsolete production lines open. To mitigate this, the military executes life-of-type buys, purchasing every single chip they anticipate needing for the next 40 years, all at once to ensure availability. But if these stockpiled chips degrade or run out, you cannot simply plug in a new CPU without rewriting millions of lines of custom, complex flight code. This technological debt has pushed the Pentagon into a critical race against time called TR-3, or Technology Refresh 3, a desperate attempt to modernize the jet. TR-3 is a high-stakes, multi-billion-dollar brain transplant designed to give the F-35 25 times more processing power, allowing it to run advanced AI-assisted targeting software. But integrating modern silicon into a 20-year-old airframe is like trying to install a high-performance Tesla engine into an old wooden horse. Carriage without any modifications, the TR-3 project has devolved into a nightmare of delays and massive cost overruns, requiring engineers to completely redesign the cooling and power distribution systems from scratch. Because of these software integration bottlenecks, the military recently refused to accept new deliveries, leaving hundreds of newly built aircraft stranded on tarmacs for over a year. The geopolitical consequence is severe. As threats escalate in the Pacific and Europe, this delay creates a two-tier fleet with vastly different combat capabilities and effectiveness. The U.S. Air Force is left with a fragmented force, half the fleet upgraded with modern brains, while the other half remains trapped in the processing speeds. As military analysts, we must expose the deepest, most terrifying vulnerability of this legacy reliance: the supply chain shadow that haunts every piece of silicon used. Because the United States no longer dominates global semiconductor manufacturing, the Pentagon must rely on third-party commercial foundries to produce these older legacy batches of chips. Older chips are significantly easier to reverse engineer, clone, and manipulate. This opens an exposed flank for the hardware Trojan, a malicious circuit hidden deep inside. If an adversary implants a hidden vulnerability at the hardware level during manufacturing, no software antivirus on Earth can detect its presence or neutralize the threat. In high-stakes electronic warfare, a targeted radio frequency could trigger this hidden kill switch, blinding the pilot's screens or feeding ghost targets into the sensor fusion. This completely neutralizes the jet's stealth advantage. The Achilles heel of modern air power is not a physical crack, but a tiny sliver of outdated silicon. We are entering the dawn of software-defined warfare, a historical shift proving that in the digital age, a fighter jet's value is determined by its processing power. The F-35 remains a masterpiece of aerospace engineering, but it serves as a stark, expensive lesson for the entire military-industrial complex about the risks of the past. We solve these complex equations so you can see the cold, hard reality behind the defense headlines. If you want to crack the code, follow GeoGrid Intel. Hit the notification bell to stay ahead of the curve. Until next time, look beyond the surface, analyze the data, and stay vigilant out there. Consider the massive financial commitment involved in maintaining these legacy systems, where every single old chip becomes a precious, hard-to-find resource for national security. The human factor cannot be ignored. Pilots must trust that their hardware will respond instantly, even when the underlying technology is decades older than they are. Global politics and industrial capacity are now the new front lines of defense. The ability to manufacture advanced silicon is as vital as building aircraft. Protecting these systems from the harsh environment of space and high-altitude flight requires a delicate balance between modern performance and the proven stability of the past. The evolution of the F-35 represents the greatest challenge of the modern age: how to keep a multi-decade project relevant in a world of exponential tech. As we look to the future, the lessons learned from the silicon paradox will shape the design of every sixth-generation fighter jet currently on the boards. Electronic warfare is no longer just about jamming signals. It is about infiltrating the very hardware that processes those signals at the speed of light. The scale of the problem is immense, covering thousands of aircraft and billions of lines of code that must all work in perfect, unfailing harmony. Innovation in the defense sector must now move at the speed of silicon, breaking the traditional cycles of procurement that have left us vulnerable. Today, the complexity of the F-35 software is its greatest strength, but also its most significant point of failure if the hardware cannot keep up with demand. Every link in the supply chain is a potential point of entry for those who wish to undermine the technological superiority of the United States Air Force. In the end, the pilot's life depends on the integrity of a few grams of silicon, manufactured years ago in a factory that may no longer exist. This is the reality of modern combat, a blend of high-speed aerodynamics and the slow, careful management of aging digital infrastructure in a hostile world. Sensor fusion is the miracle of the F-35. But it requires massive computational power that pushes these legacy chips to their absolute physical and logical limits. We must reclaim the lead in semiconductor production to ensure that our most vital weapons systems are never again dependent on the shadows of the past. Sustainability in the air requires sustainability on the ground, and that starts with a secure and modern supply chain for every single electronic component. While stealth hides the jet from the eye of the radar, only the internal processors can keep it hidden from the more dangerous eye of the hacker. The race for the TR-3 upgrade is not just about power. It is about the survival of the stealth concept itself in an era of AI-driven detection. Bridging the gap between the 20th and 21st centuries is the most expensive engineering project in human history, with the F-35 as its center point. The sound of freedom is now the sound of data processing, a silent battle fought in the nanoseconds of a processor's clock cycle during high-speed flight. As we build the next generation, We must learn from the silicon trap and design systems that can evolve as fast as the chips that drive them. Every mission is a test of both man and machine, and today that machine is only as good as the oldest chip on its main circuit board. Electronic resilience is the new stealth. Without it, the most expensive aircraft in history is nothing more than a target for modern digital age adversaries. The story of the F-35 is far from over, but the Silicon chapter will be the one that defines its legacy for the next 50 years of flight. The path forward is clear. We must innovate, integrate, and secure the digital heart of our defense before the technology of yesterday fails. The challenges: look beyond the steel and the speed to see the silicon reality that governs the modern battlefield. This is the new age of electronic warfare and survival. Thank you for joining us on this deep dive into the hidden world of military technology. Stay tuned for more insights into the future of global security. If you found this analysis valuable, support our mission by liking this video and sharing it with those who want to understand the true cost of defense. Stay informed, stay vigilant, and always look for the data behind the headlines. GeoGrid Intel is your source for the truth in a digital world. The Silicon Paradox is just the beginning of the story. There are many more secrets hidden in the hangars of the world's most advanced air forces. We will continue to track the progress of the TR-3 and the evolution of the F-35 fleet as it faces the growing challenges of a new era. The future of warfare is here, and it is being written in the microscopic pathways of a processor. Make sure you are ready for what comes next. Thank you for watching GeoGrid Intel, your window into the hidden technology of the modern world. See you in the next mission. Stay alert out there.